Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
About electrochemistry.
Yes, indeed.
I'm your host, Dr. Alex Preff. I'm here with Dr. Neil Spinner, and hopefully you'll also be joining us later as we launch our podcast in a few weeks on YouTube for our Tier 1, Tier 2 members. Actually, no, I think it's just Tier 2 members. Tier 2 members will get an early glimpse of the Electrochemistry podcast, which will be coming out December 7th, and then just a general launch for everybody else in beginning of January.
Yeah, the 4th or something.
I think it's the 4th.
It's 2 numbers, and somehow we have an impossible job of remembering what those numbers are. It's December something and January something. Even though we control those dates, we still don't know what they are.
Yeah.
We hope
they're a Thursday.
Exactly.
We decided it would be a Thursday.
Yes, that's correct.
But welcome everybody. Welcome Chris, and welcome to another episode of Ask Us Anything About Electrochemistry. This is where you have an opportunity to ask us any questions you have on electrochemistry. We have YouTube videos and webinars and over the phone, and this is just a better platform, streaming and asking questions live to kind of dive into some of the questions you have about electrochemistry. Now, I think this may be 30 episodes or so.
I think it's like 31 now.
Maybe 31 episodes now. We have discovered that to help you understand as much electrochemistry as possible, the things that are really important in the questions that you ask is that the questions are not so generically broad, such as what is cyclic voltammetry, or explain everything about cyclic voltammetry, or explain EIS, right? We have full-on webinars for Tier 2 members on our YouTube channel that are like hours and hours long that you can listen to or watch to answer those types of questions. But then also, if your questions are so specific, like, that you're really looking for a constant or a number associated with a very specific reaction, we're probably not going to be able to help you with that. But if there is something about the fundamentals that you're on the fence about, or there's a concept that you're trying to wrap your head around, this is the best case situation. Like, you can ask us those types of questions, which we should hopefully be able to answer. But of course, you guys always surprise us with new things anyway. So we usually run this live stream for about 2 hours. And during that time, we can take as many questions as we can. We are using Restream as the platform to distribute this. So it's on YouTube. It's also on Twitter. So if you're on Twitter, you can also ask questions, and we check Twitter. We're being better at checking Twitter and YouTube for all the questions that come in.
Were we ever bad?
I don't think we were ever actually bad at checking questions,
but we can still be better.
We can still be better. We can always be better with checking and answering questions about the subjects. Also, if you're listening to this after the live stream, there should be we'll have links in the description below to the specific questions if you want to go directly to the question that most interests you. So that will usually happen a couple days after the live stream has been broadcasted.
And also, as a note, we will be off next week. It's Thanksgiving in the United States, so we're not working next Friday, frankly. So we're gonna leave you to your own devices next week. So
yeah,
you
continue to come up with questions.
Yeah.
The following week we'll have them.
We'll be back the following week. But as I hope everybody has a good, for those who are US based, I suppose, have a good Thanksgiving holiday next week, and after this week, we'll be back in 2 weeks. So.
Yes. And also, speaking of which, the following week, we will be at the MRS meeting in Boston.
Ah, that's right.
So if you are in Boston or near the Boston area or are attending the MRS meeting, come visit the Pine Research booth. I believe the booth number is like 423. We'll be there during the exhibit hours. Of course, if you just want to meet up with us for like dinner or lunch or something, we're always happy to meet fans and people who like to watch the live stream. So that is the week of November 27th is when the MRS meeting is. So that's another opportunity to kind of talk to us and meet us and just what our schedule is.
Exactly.
As we're all over the place.
So before we get to any new questions, which if there are any, please go ahead and type them or post them on Twitter. As Alex said, there were a couple of questions earlier in the week on this event that were typed in by Fernando, who I think I was out last week, but you asked, joined last week and asked you some questions. So the first one here, just as a sort of I have somewhat of a logistical thing as far as publications are concerned. And so this is sort of a general answer to anybody who might be using our software. I suppose if you're publishing and you're kind enough to use our software and want to report that, first of all, thank you very much. That's very nice. Obviously, as we are aware that publications are the currency of our craft, right, of the scientific community. So any and all mentions of our company in the scientific research, we're very grateful for that. So the question that Fernando asked was, for an article, is it enough to put the aftermath software and the materials and methods? Is there an article to cite? Yeah, that's perfectly fine. There's no, you would explain that you used, Pine Research aftermath software in the same way that you would explain you used like anything else, right? We used a Pine Research this, or a Gamry this, or an Autolab this, whatever you would use to describe. And then sometimes, this depends, right? Every journal article and every writer might handle it differently. Like when I was in school, I used to write something like, I used a Metrum Autolab potentiostat, and then parentheses, I'd put maybe the country where they're located, like the Netherlands or something, or you'd put Pine Research, United States. Like sometimes that's a thing. Anyway, the point is there is really no set for this. You do it however you like, and if you are kind enough to reference our software, we just appreciate it at all. And yeah, that's quite nice. I don't know that it's actually that common, at least from what I've seen, that people list the software when they talk about the analysis they do. Most of the time it's the hardware, where they get the chemicals, Sigma Aldrich and Fisher and wherever, right? So it's greatly appreciated if you do mention our software. We do work very hard on our software, to be honest, and we update it as much as we can, and we put these features in. So we're always appreciative when people will cite it, I guess.
Yeah. I mean, it's also like you're using it for the analysis, like circuit fitting values,
right?
I think it would be in the same regard if someone was doing DFT or used COMSOL or MATLAB to create something. But yeah, it's like if you're using Origin or Igor to do your data analysis or to create your plots, no one ever really cites those those pieces of software. They
Yeah.
always cite just the whatever it was used to make the calculation, sort of say.
Yeah, just gets taken for granted. So
Yes.
if you don't want to take us for granted, we appreciate it.
Yeah, we appreciate it.
Yeah.
Copy citation. So Chris is just mentioning, might be worth adding. Copy citation button to the about this software dialog. Yeah, maybe.
I suppose. Yeah. Honestly, the about thing, I'm not sure that has been changed in 45 years, and our software is not even 45 years old. So yeah, that's one of the parts of a software coding that you don't often even think about much. And then yeah, it's not a bad idea to have like citation. But really, honestly, it's like well, now I'm dipping into a slightly different aspect of this, but like our company's name is Pine Research Instrumentation. That's the name of our company, right? But before 2005, we were Pine Instrument Company only, like, and we still are Pine Instrument Company. That's like our factories in Pennsylvania, and so that's our name. And it's like over under 75% of mentions of our company, literally anywhere, it's never Pine Research ever. It's Pine Instruments, which is also not the name, right? It's anyway, I'm not it's just one of those funny things. It's like our actual company name is very rarely like properly written or whatever.
Written.
So we're used to, if someone puts Aftermath by like the Pine Company, that's fine too. I mean, that's not, I wish you would put a real name, but we're used to our actual company name not exactly being accurately listed. It's just the way, it's just the nature of the beast, I guess.
Even just some of our instruments, some people call like our potentiostats like the Pine Box.
Pine
Box. It's like, no, it's either the wave driver or the wave now with a number associated with it.
We have never sold a Pine Box, but that's okay.
I know.
There
is a part of me that feels, I was thinking about this, like we went along with the whole like Aftermath software, but originally, this is a little bit of history. One of our old purely analog potentiostats called the AFCBP1, it was controlled by software called PineChem.
Yeah.
It was called PineChem. And it was like, I thought it was like real simple. Like you could clearly tell which company it was and who did it. And I'm like, why didn't we just create, like, why is it called Aftermath? Why don't we call it like PineChem 2? And then we have like, and we'll have a PineChem 3 coming out. And that it's just like super clear where the software came from. But no, we have to have Aftermath.
We lost out. I never actually thought of that, to be honest. But having the name of our company in the software. But I guess you have to think, I'm trying to think like, I don't want to just list but actually quite a lot of, now that I just think for a second, actually quite a lot of our competitors' software names also do not include, like Biologic is EC Lab.
Yeah.
Right.
Yeah.
Metrum is Nova. Gamry's is Framework, although it's called Gamry Framework. But like, it's actually, this almost feels like either we're doing it right because everyone else also doesn't have their company's name in the software, or we're all doing it wrong because we're missing an opportunity to have our company's name be part of, the software as a branding thing. It's kind of interesting. I mean, we're like stuck with Aftermath. It ain't going anywhere, but I think that, I never really thought about that way, to be honest.
I mean,
I think you have a good point though.
I mean, we work for the sales team, and so I think about sales and marketing like all the time. So these types of things always come up.
We should do a Pine Box release in the shape of a coffin. Maybe for Halloween.
Shape of a coffin.
Maybe for Halloween we'll do a Pine Box, and it'll just be a coffin shaped potentiostat. Is that too morbid? I think there's a certain like segment of just humanity that would find that hilarious, right, in a very morbid way, and a certain segment of the population that would be absolutely horrified. And I salute both of those segments. Sorry, we got a little off topic here, which was kind of fun. But there was one other question by Fernando.
Oh yeah.
In addition to just the citation of our software, and so he asked, "Can you give some ranges for circuit element values for SPE screen printed electrodes or electrodes of that size? Not something specific, just to give me an idea that the numbers also make physical sense." Well, I actually can give you something specific. And well, frankly, if you're asking for a range of numbers, that is actually specific. So I'm happy to try to do that for you. Generally speaking, a screen printed electrode is likely to have a moderately decent, if you will, capacitance with a relatively low resistance. And that's because the screen printed electrode is has a, well, so I guess it depends, right? But they can have larger surface areas. It depends, right? Some of them are smaller, okay, but sometimes screen printed electrodes have a decent surface area because you're trying to get, like a biosensor, and so you want to have a decent amount of surface area to be able to like get enough current to sense a thing, okay, whatever. So, so that being said, it's like you might expect capacitances, and this might be in the form of a CPE. So I'll just use the unit farads, but in reality, a CPE, the units are it's a wonky thing. It's like, ohm to the ohms over seconds to the alpha, something crazy like that. So, right, because there's an alpha,
Yeah.
right? So I'm just going to say farads for simplicity's sake. So basically, I would expect circuit element values for capacitive elements to be in the range of microfarad to millifarad at most. Probably not tens of millifarads, probably not less than a microfarad. Although I suppose it's possible. I mean, nanofarad levels aren't unusual, but for an SPE and for electrodes of that size, now again, I'm assuming a size is like moderately decent surface area for sensing. But if you have a really small SPE, you might get to like nanofarad level. But probably is my guess is something firmly in the microfarad range is my guess. And then as far as ohms are concerned, for like resistances, you're probably talking about a kilo ohm at most, max. You're probably talking tens to hundreds of ohms. But of course, it depends on the resistances you're talking about. And this is the last thing I'll say about it, which is to say that I would expect if you have good connection and you have a good electrolyte, of course, it depends aqueous or non-aqueous. Let's just pretend you're using aqueous electrolyte, and let's just say it's a relatively, decent enough concentration, 1 molar or something, or 0.5 molar or whatever. I would expect tens of ohms at most for like IR drop uncompensated resistance, that kind of thing. Where it gets tricky is that like if you're looking for a range of resistances that you're going to get, that depends entirely on whatever process you're studying, right? You might be studying a process that's very depending on what your overpotential is, because resistance will decrease as overpotential increases. The more driving force you have to do your reaction, the lower the resistance is. So your resistance could be anywhere from kilo ohms to single digit ohms, depending on how easy or difficult the reaction you're studying is, how much impedance there is. But generally speaking, I guess that's a reasonable set of ranges for you for the capacitive and the resistive elements, if that makes sense.
All right.
Okay, so
we have a couple questions that have come in.
Yeah.
All right. Also, hello. Good to see you again from last week. If you have any questions about the Nernst equation, which hopefully you don't because I went over it in a lot of detail. But continue to ask questions. Hope your exam went well. Next question from Ejazul Bashir. While doing heterogeneous catalysis, sometimes the reverse scan in CV crosses or intersects the forward scan at a certain potential. What could be the possible reason? And there's a little bit more information. Chris asks what species is involved in the system, with which the response is using aqueous solution of KCl. So reacting species are H2O and H plus ions under reduction potential conditions. Okay, so just so everyone kind of knows, and I'm gonna let's see, just to kind of get a kind of a semblance of what that. I'm gonna minimize this for now, but But when I think about this, what you're looking at, or what you're specifically talking about, is a situation. I'm going to be using the IUPAC convention for plotting this. So if you are reducing something at negative potentials, and you're going to get a negative current, so let's say this is like 0 or something. So you're sweeping, and then you have this like exponential decrease But then on the scan back, you have some kind of curve where it goes this way instead of going like this way, right? That's what I'm assuming, right? I'm assuming that you have some kind of intersection on the reverse scan with regard to doing this experiment. Now, I've seen this kind of stuff before. I'm not 100% sure about what exactly it is. From just a very simple, just kind of looking at exactly what that is. It's just current at that potential is lower, sort of say. It's lower, and again, lower meaning more negative. So it's lower than the potential when it first starts. So if you're doing heterogeneous catalysis, there's a possibility that the reaction is still happening quite efficiently at that potential. You're getting let's see. So I'm just trying to think a little bit more about this. So it's going, and then, or actually no, it's going here, and then it ends at a current that's more negative. So it's like it's still doing some of the reaction, or there's some surface species. Usually, I suspect that there's some kind of surface reactions that are occurring, and what was supposed to get oxidized off, because as we go to more positive currents, we're oxidizing, didn't fully get oxidized off. So there's also, if it's also in this region, depending on where that intersection is, it may be a different formation of the electrical double layer as well. Like the charging current could actually be different. And especially if you are reducing protons to hydrogen, there's H plus, there's the hydrogen, but there's probably adsorbed hydrogen on the surface, and that also affects the charge. So I've seen stuff like this before. I don't know if that's at least my initial guess or hint about what's happening, but please leave a comment if you have further clarification, or if you or it's like, oh, that makes sense, or oh, it's not good, or something like that. So,
I think the other possibility,
mhm.
as far as that's concerned, is something like pseudo reversibility can cause odd stuff like that to happen, because I find it hard to just describe it too. I didn't see it much.
Yeah.
Like when I was in graduate school, I did see occasionally this kind of odd thing where you have a weird hysteresis or you get a crossover.
Yeah.
There's certain fields where people talk about it in differently, like if it's in an ORR or it's in an HER, like it might mean it might mean different, it might have different consequences or arise for different reasons depending on the field of study, like the specific electrochemical system you're studying. But like in a pseudo reversibility kind of a thing, it's like it's not like it's almost like if it, whether the way Alex drew it exactly is, but it's like if the one trace doesn't, like it should go down, you know what I mean? Like if it should go down more, but it doesn't. And so it crosses over the positive sweep. And so it's like, it would have dropped down to a reductive current more quickly if it was more reversible. And so it isn't. And so it takes, and I'm like drawing in the air. Let me just share.
But that's actually a good point, because hydrogen that's left the surface.
Yeah. And actually hydrogen is a good example of this, because in the hydrogen evolution, or sometimes the oxygen evolution reaction, the hydrogen evolution in a CV, am I sharing? I think I am, right?
Yes.
So like sharing. As you go, this is a CV. So this is voltage and this is current potential, whatever. So as you go, let's just say more negatively, a lot of times with the hydrogen evolution reaction, you might get something that it starts dropping, but it's like, it's not always smooth. You have bubbles forming, you have hydrogen forming. So it's not always as smooth as this, right? And then it's like, as you come back up, it might sometimes cross over. Sometimes it'll cross like multiple times if it's kind of just a mess. And that's just like, sometimes it's just noise because of hydrogen evolution. But like the pseudo reversibility thing I'm talking about could be something of a phenomenon where you have like, I'm going to try to draw this, and I'm hopefully I don't butcher it, but like, if you have this like peak or something, and then it comes down, it's like, if this was perfectly reversible, right? Like in theory, it would, I don't know, dip down and you get the reduction or whatever. But if it's like pseudo reversible, it's not reversible. What could happen is that like the negative peak is like delayed. And so there's a crossover before the reduction can finally happen. You see what I mean? And so it's like right here, you get this crossover effect, but it's almost like an artifact of a pseudo reversibility, that it's like it should reduce here, but it doesn't until 50, 100, 200 millivolts later, something like that. And so that can also be a mechanism thing. Like there's EC reactions, EEC, EC, ECC, EEC, EC. Sorry, I'll stop. So different mechanisms of that. Like if there's a chemical step that's interfering with some of the processes at the surface, that could delay the reduction or oxidation or what have you. So those are some of the like very general reasons, I guess you would say, why some of this might be the case. So I hope that's I don't know. That's a decent.
Hopefully that gives them some ideas about what could be happening.
Exactly. All right. There. Let's see here. I want to see something. Random. Okay. There's the next. I was also preparing some data. That's why I was a bit distracted here. So this next question from Daniel. I was getting some stuff ready to kind of show you. So Daniel Gamero says, I have a question about the Mott-Schottky representation. What is the meaning of the parallel versus the in-series representations? So this is a good question. Mott-Schottky. So what I'll do is I'll share a bit of background and then I'll try to answer your question directly actually first. So the answer to your question directly is that it is how you choose to represent the space charge capacitance. And it's as simple as when you do Mott-Schottky, you are basically studying the space charge capacitance of a semiconductor, right? And it is generally regarded that you have two possibilities. It's just that you can you always have some impedance or some resistance present, okay? And so it's either in series or in parallel, the space charge capacitance with I don't know if it has a special name, if they call it just resistance or space charge transfer resistance or whatever, but this is basically your space charge capacitance, right? Whether it's either one of these capacitors. And so what the difference between the two is, it's really just mathematical, actually. I wish I have it on my board in my office upstairs. If you do the mathematics, right, basically like Z of the series model is equal to the resistor, the impedance of a resistor is R, right? Plus basically 1 over J omega C space charge. So that's so basically what we have here is a situation where we're trying to solve for this, for the space charge capacitance, right? That's what we're after, the capacitance, because in a Mott-Schottky plot, we are actually plotting 1 over C squared versus the voltage. And we get, usually you get something like that, or it's the other direction, depends if it's an entropy type. And you get the slope and you get your flat band potential and your electron donor density. The point is that how you calculate this C depends on whether you're assuming that the space charge capacitance is in series or parallel. Now, the trick with this is that if your frequencies, and this is sort of, as we have come to, at Pine specifically, investigate, this is actually not the best line of thinking. I'll explain why. But as best I can tell, this method that I'm talking about right now, which is why your question is related to which one of these models, what does it mean? This approach to doing Mott-Schottky, as best I can tell, is one largely propagated by folks like us in industry. And that is because you typically have a method of attaining the space charge capacitance by picking one or a very short range of high frequency points and just doing it in quick impedance at each voltage. Okay, and so basically the math, right? To finish this mathematical bit here is that the parallel, it's different, right? The Randall's sort of void element here, the impedance is 1 over that is equal to 1 over R plus J omega C. So it's basically an inverse. And so now in the second case, when you solve for C, obviously you'll get a different result. And so effectively what happens is that when you do impedance, if you do one frequency, you get a Z real and you get a Z imaginary, right? And I'm not going to go through all the mathematics right now. It's a little more effort than I want to talk about in this setting quickly here, I suppose. But basically, whether you do series or parallel, you assume a series or parallel representation, you can get a Z real and a Z imaginary, right? Because that's impedance, right? The impedance can be broken down into real and imaginary parts. And effectively, you'll just have to take my word for it. It is actually possible to solve in both of these cases for the space charge capacitance as a function of both Z real and Z imaginary. Okay. I don't know if I could find the equations quickly. Effectively, what happens is that and it's a function of Z real, Z imaginary, and frequency. And as frequency is infinity or very large, they basically devolve to the same equation. So effectively, if you choose one frequency that's relatively large, like kilohertz or higher, usually something in that range, the calculation of the space charge capacitance, whether you're assuming a series or parallel model, is basically the same. They start to deviate as the frequency drops. Now, here's the part that's the problem. This is not a good way to do Mott-Schottky. Fundamentally, it's not. Okay, so a Bode plot for a system like this, for the magnitude of the impedance and the frequency, might look something like this, or it might just go up forever. But effectively, when you choose one high frequency point, you're choosing something around here, around here, around here. But if you know anything about capacitive elements, this straight line right here, this whole section, that's what a capacitor results in on a Bode plot. So actually, what you really ought to be doing if you're doing Mott-Schottky is taking a range of frequencies in the mid to high range, or just the middle, window of frequencies, and getting your capacitive element from a fit of this diagonal line. Basically, that's a more effective way to get. I mean, it's like a circuit fit, and it actually renders the need to care about the structure of parallel or series. It renders it mostly irrelevant, actually. And so here, what I'll do is the last bit that I'll kind of talk about here is that I'll show you our software. So the possibility for Mott-Schottky in most companies' softwares is this. It's just a single frequency. So you pick an amplitude, like for any impedance experiment, you have a range of potentials you want to go and do your Mott-Schottky at, and you just pick a frequency. So you might pick 10 kilohertz or something, and you can repeat it, whatever. But that is, as I said, not terribly accurate. And actually, we've done some testing. I've done some testing on this, and it's actually fundamentally less accurate to do it this way. It just is. You get much less accurate results when you do a single frequency, like based on real experiments where I can set up an experiment where I use a capacitor of known value, right? And so in theory, when I do my Mott-Schottky, it should spit out the capacitance of my capacitor, right? Or changing capacitor, whatever it is. And it's like doing a single frequency, you get much less accurate than if you do a multi-frequency. So in reality, what you want to do, in my educated opinion, I would say, I mean, other people might argue otherwise. Maybe it's quicker. Maybe there's reasons why single frequency is acceptable in some situations, and that may be the case. But in my suggestion and opinion is that you should do a short range of frequencies. You're basically doing a incomplete but short EIS experiment over a range of frequencies. So you might do like 10 kilohertz to 10 hertz. You can just do like 3 points per decade, like a short, maybe 5 points, whatever. You can do a short impedance experiment at each voltage. So it's really just like a step impedance function. Instead of like one frequency at each voltage, you do a range of frequencies. Change the voltage, range of frequencies. Change the voltage, range of frequencies. And at each of those voltages, the range of frequencies, our software, for example, in this mode, multi-frequency, will fit properly the line, and it will give you the measure of the capacitance, the space charge capacitance, as well as the in this case, for example, I don't even know what this data was from, so this data might be terrible, but it's just an example data. So you basically, these capacitances are measured like this. So you're getting the slope of that range of frequencies, okay? And then you get your Mott-Schottky plot with your capacitances out of that, and also a measure of the ideality, basically. So it's almost like whether it's taking into account whether you want to fit a CPE or a capacitor. So effectively, it's like saying, well, these are the capacitance values, but actually it's somewhat non-ideal as well. And so you can get, this was like a point. So this, again, I don't even know what particular system this was. This was just some example data that I had collected internally for our development purposes. But you can see those are the kinds of data that you can get from a more complete analysis using Mott-Schottky. So please follow up, Daniel, if you're still listening. If you have any follow-up questions. Oh, I guess there was a follow-up question. The second question would be, okay, we'll address that in a bit because it's a slightly different topic than that. If there's a follow-up, but anyway, I hope that's helpful to kind of give you a bit of a overview of Mott-Schottky. And the takeaway, I hope, is that if you're doing Mott-Schottky, my suggestion is to do a range of frequencies and not a single frequency, even though many companies, and in fact, Pine, originally, that's what we did offer, was a single frequency. And then we sort of realized, actually, I don't think this is the most accurate way to do it. So we've adjusted our software, somewhat recently to include a range as the best option. Okay.
Very, very good. Moving on. There's a lot of other questions coming in. From Tanya Kashari. Hello, sir. Why we need to do DPV and OCD if we're performing CV?
What's OCD other than obsessive compulsive disorder?
Yeah, I think we might need a little clarification.
What's
it might be
OCD?
OCP, possibly, is maybe the open circuit, maybe.
Yeah.
But the answer is you don't. You DPV and CV, you don't have to do those techniques if you're performing cyclic voltammetry. OCP is helpful in just understanding what the open circuit potential of your system is and making sure it's not changing dramatically during your experiment. But DPV is a different technique to CV. In some cases, it's a better technique because it removes things like capacitive effects from your data, and you're mostly left with just Faraday current. It just takes longer to do. That's all. I mean, that's really the only major drawback to DPV. So, but if you have further questions about that, I think it'd be tough to go into detail about DPV and OCP. But you don't need to do those techniques if you're performing CV.
I should say the only way you would need to do OCP or OCV is if you are trying to do CV with any of your potentials with respect to OCP.
Yeah.
Like sometimes you want to sweep from OCP to 200 millivolts up above OCP or whatever. Like obviously if you're using OCP as your reference point, well, you have to measure it.
Yeah.
Like that's somewhat obvious, but yeah, fundamentally Alex is correct. Of course you don't have to, you can just run it CV by itself. You don't have to run the other ones. So.
Yep. So let us know if you have any further questions about that, and we'll move on to the next.
So yeah, Daniel had a follow-up, but it's possibly different, so I can address this.
Yeah.
Electrochemical noise. A second question would be about the electrochemical noise measurements using the bulk electrolysis in ZRA mode. Is it possible to perform the experiments in a 4-electrode setup at a liquid-liquid interface? Yeah, it is. For sure. So electrochemical noise, for those who aren't aware, it's usually a technique that's used with in the context of corrosion. I have some doubts or thoughts about it in some general sense. I find it to be a bit of an odd technique as far as drawing conclusions for a couple of reasons. Maybe I'll share those later if there's follow-up questions about them. This might be another trigger point for me, but but fundamentally, that is what a ZRA, an electrochemical noise measurement is. I don't know that it necessarily requires a 4 electrode setup. I suppose it can. But you can do 4 electrode in liquid ligand interface. I just don't know that it's going to matter. So, for example, separating the working sense and the working drive in a liquid interface is probably not going to have a material impact, because if you're in a strong enough electrolyte, it's like, I don't know what difference that would make. Everything's all sort of connected, in solution. A 4-point, but separating the working drive and sense lines, I guess, if you want to. I guess the example, maybe I should take that back. The example is like a membrane test. There's like Lugin cells you put on either side, and that's a 4-point measurement. So perhaps that's perfectly fine. And yeah, in general, it's something you can certainly do. A ZRA mode, zero resistance ammeter, it means that you're basically, the potentiostat is it's effectively setting 0 volts between the working sense and the reference, and it allows whatever current will flow as a result to flow. It's a dangerous experiment in some situations. Like if you did it with a battery, it's just setting 0 resistance between anode and cathode, and it's just immediately discharged. So you're going to get a ton of current. But in a liquid setting, that doesn't happen exactly. And so you'll get usually some amount of noise, right? Hence the name. And then basically the analysis of these results involves doing something like discrete Fourier transform or fast Fourier transform, or a method called maximum entropy method, which is just another mathematical algorithm that deconvolutes the noise into some characteristic frequencies or what have you. And those are used to draw conclusions. And maybe I'll just add my own little editorial, is that I have doubts about it, frankly, because I find it hard to decouple exactly whether it's almost like there's an assumption being made that all of the noise you observe during a ZRA test in this way is because of all of the surface fluctuations and whatever. It's like, it's also just probably like instrument stuff perhaps. And like, if you're not properly grounded, it might be just noise from lights and AC mains. And like, there's a million different things that might contribute to like odd fluctuations in noise in your data. And usually we're interested in signal to noise being good, right? And there's something implicit about an electrochemical noise experiment where you're interested in the noise, only as compared as the signal. Yeah. And so it's almost like I don't see a lot in the literature, and maybe I admittedly don't know it like super well, but I don't see a lot of like, well, let's deconvolute the noise that is, we know from the surface processes, like there's some noise associated with that. And so we're getting information about the corrosion or the surface process happening, versus noise from just all of the things that contribute noise to an electrochemistry experiment. Like, how do you know? You don't want to study that. You don't want to study the noise that's coming from the potentiostats filter settings. Like, no one's like, that's not right. Like that's completely extraneous. So I'm somewhat dubious of this technique to some degree, but I do recognize that people do use it. And in general, the answer to your question is you can probably do that. And the sampling rate is usually hertz to kilohertz at highest, so you don't need to sample too fast. And then whatever the analyses that you want to do on your data after that, you could likely do. So
all right, next one is from Stephen Boyd. We spoke on the phone, maybe it was a week ago or 2 weeks ago. I've been getting pretty busy, so good to hear from you again. I did take a quick look at Kevin Lamb's paper. The supplementary information is massive. You're right; it's like 200 pages of molecules that they electrolyzed. But I can't honestly say that I went into it in a lot of depth and detail. But your question is that so recommend you don't necessarily have to use a potentiostat to start doing organic electrosynthesis, but you're using a DC power supply and you're getting a good current transfer. But so are you, quote, allowed to use the voltage and the current data to calculate R on the fly? And I would say probably not. Maybe, generally speaking. Let me explain kind of what I mean. So right now what you have, let's see, and I'm showing up here. So let me erase this. So what you have is you have a power supply. So this is some kind of big voltage box. All right, some voltage is being applied to it. And then you have just two electrodes, really. And those two electrodes are in some kind of solution. And so you know what the voltage is. So you know that, and you're measuring, and it's also giving you a current value. And so you can use Ohm's law and determine like the resistance. And it's true that, like, yes, you can figure out what the resistance is, but it's the resistance of every single thing in this that's going on here. And so there are elements. If you were to draw the circuit diagram equivalent, sort of say, there is you have kind of what we describe as a Randall's element, where you have a charge transfer resistance on both sides. You have some kind of double layer capacitance. You have some kind of resistance in solution between your two electrodes. And then you have another double layer capacitor, and you have a resistance. So the resistance that, and this is bad, not a good resistor. So the resistance that you measure from looking at these values encapsulates all of these things. Now, how much, like maybe most of the resistance is here. You may be able to make a very good estimation that, like, hey, the current is flowing through this resistor and this resistor. These things are charged, and maybe these values are super small, and hence this value for R is actually like the value that you get for R is indicative of the solution, mostly indicative of the solution resistance of the entire thing, because who knows how much voltage you're applying, but the charge transfer resistance at the voltage that you're applying may be so sufficiently high that the RCTs, the charge transfer resistance for both processes happening on both sides of the electrode, may just be super small, because those values will change as a function of the voltage that you apply. So that means that your DC power supply, depending on what you can do with it, but you may find that you're not going to actually have a linear relationship between the voltage that you apply and the current that you measure, because this resistance value will actually be different if you apply a too low of a voltage. These guys will actually get kind of high. No Faradaic electron transfer process occurs. So that's just kind of a interesting electrochemistry thing. But that is what I would say with regard to estimating your R value with just a 2 electrode system and a power supply. So hopefully that that makes sense. Okay. Let's see.
So there was this question that Chris also clarified. Do we have any recommendations for books to read about this? And I don't know what you mean by this. Is probably when we were talking about whichever of the last questions. Yeah. So I don't remember. I don't know if you mean electrochemistry in general, or it was what the Mott-Schottky thing, or Alex was talking about the crossover thing. So I don't know which exact topic you're referring to. But yeah, I mean, the short answer to your question is what Chris said, which is that everything is math, and so you can't escape it. And so unfortunately you are now resigned to your fate, I suppose. But more to the point, I guess, is that there are not, I think this is mostly true. there are there's a gap, I guess, at least it seems to me, which
Mhm.
in the resources and perhaps just literature in general for like practical stuff. Just there's brilliant textbooks like Barton Faulkner's, and there's Orism's textbook on and Lassia's textbook on impedance spectroscopy, and I don't know if there's any specific ones on Mott-Schottky. I would assume that Orism's book has a section on Mott-Schottky because it's an EIS technique. To be honest, I don't know off the top of my head. I think it's in there. And all of this stuff is I mean, they're brilliant, but yeah, they are heavily fundamental and mathematical. And I've described this phenomenon. I always feel like this is the case where it's like, even if you're like a competent graduate student or postdoc or whatever, if you can have a class, you can read a book, you can do all the kinds of things, right, to like educate yourself about the equations and everything. And it's like everybody reaches the point where they're standing in the laboratory at the equipment, at the computer with the electrodes in front of them or whatever, and they're just like, I forgot everything I read. Like it all goes out the window. It's like the practicality is the thing that's just the heart. And to a certain extent, I do think, unfortunately, and I think I say this many, many times when I talk with folks, either on this, in this Ask Us Anything on live stream or in person, if I do like any of those kinds of panels where help graduate students with career focuses and future paths and all those kinds of things. I've done those at conferences at times. There's a certain degree to which the answer of like, how do I get better at XYZ is that like, go in the lab and do it and you're going to fail. Like that's just some of the answer is just always that. So whether it's this person here or it's anybody in general, like your thirst for knowledge and desire to learn and desire to get more materials about anything is admirable, and an excellent like line of thinking, I would say, on it truthfully. Like I really mean that. I think anybody should be applauded for wanting to learn more, like full stop in general. But to a certain extent, a lot of the practical field of electrochemistry research, the answer is you have to just get in the lab and bang your head against the wall for a while. Like there's almost no substitute for that, it's it's just kind of the reality, right?
Well, yeah. I agree. I think that there is no there's a fun like little analogy, which is like you can read and you can study how to swim. You could read the best books on swimming, the best technique, all those types of things, but absolutely nothing's going to prepare you for swimming besides getting into a body of water.
Yeah.
Like nothing can prepare you for that. You have to experience it. It's knowledge associated with just doing the thing. And that being said, you will what I have found is it's probably an iterative process. You read something, you do something in the lab, doesn't work. You go back to reading. You figure out, oh, maybe I should have done this instead. You go back into the lab. You do another thing. You hit another stumbling block. You talk to somebody about it. There's many ways to kind of learn this stuff.
That's a good way to think about it, actually. Yeah, it's an iterative.
Yeah,
process,
you may need to iterate between the two.
Yeah.
I will share. I similarly agree that I think that most electrochemistry books are absolutely, well, they're okay. They're textbooks. They're really textbooks. They don't get around describing things conceptually. But this book might be helpful for you. I think I'm sharing my screen. It's called Electrochemical Analytical Techniques in Electroanalytical Chemistry, or sorry, Laboratory Techniques in Electroanalytical Chemistry, by Pete Kissinger and Bill Heinemann. I used this book when I was in graduate school. Like I had a few books. This was my favorite because there's actually not that much math in it comparatively. There's lots of pictures and diagrams, usually described for instrumentation, because this is about doing stuff in the lab. Now, granted, a lot of these pictures are literally written from like the 1970s, where it looks like it's a military report, you know, from like when they were working on the atom bomb or something like that. It's just like super, super old looking like diagrams. It's not a SolidWorks rendering or anything that we would professionally have in our like, you know, database or something. So, but that book, Laboratory Techniques, I think it has less math, but hopefully helps you understand some of these things conceptually.
Yeah. I think that is a good assessment of it. I mean, and that book, perhaps, you know, outdated at this time, but
Yeah.
it's still a useful one there. And yeah, it ultimately is an iterative process. But you know, it really does sort of highlight again to me just that there is basically a lot of lacking in the area of practical stuff for electrochemistry. Electrochemistry still seems very much like a field where it's like there's just a lot of people who feel out like a fish out of water.
Oh yeah,
You know?
yeah. And that goes to say, and actually he has a follow-up comment, which is it'll be another year until, or maybe 3 depending on his university, until he does anything practical. So he's really just looking for books to kind of fill his time on understanding some of the theory and things like that. Okay, I can understand that. Yeah, and hey, well, I'll be honest, I'm still learning new things like all the time about electrochemistry, and and I don't know, like I think both of us are all constantly learning new things about electrochemistry, like fundamentally how certain things work.
Oh yeah.
And expanding our mind about how, like, what these things really are and how to think about them and how we can explain certain phenomena. And no one, I'll actually make the claim that I don't think any one book really kind of gets it right with its conceptual understandings. I mean, some books actually, like some really good books, are wrong in terms of how they describe certain things, and that's just because, well, I've been hanging out with Dan Shearson, who like, there's like what we learn in university and the books that our professors say we should buy, and there's the books that we're even recommending. But there's a bunch of books that are like from other countries that have like a totally different way of looking at things that I'm actually curious about seeing. The whole Russian school of electrochemistry has all this.
That would be tricky
stuff.
too if you can get over the language barrier, you know,
Yeah.
of some of this. But obviously, people in different countries are and have been learning, you know, the same science or similar science, and so there's probably differences there. And yeah, that's a whole
other bag of worms.
ball of wax.
Yeah.
Ball of worms.
Yeah.
Bag of wax.
Yeah. Yeah.
That's a whole thing for sure. Yeah.
Like I guess I'll give you like an example, something that, like, when you take in a electrochemistry course, I guess we'll get to the question soon, but if you take an electrochemistry course and they talk about capacitance and the electrical double layer, there's the description of the double layer is one thing, but then even fundamentally understanding capacitance, just what it is and what it does, and the whole world of like AC versus DC voltammetry, like there are books that just talk about things from a DC voltammetry perspective, but it's actually a really, really tiny picture of this bigger AC world. And that book, which is super thick and dense, is only talking about the small DC part of that world. And so that's been like kind of an awakening in my mind about like, oh wow, we're not even thinking about these things correctly. In some cases, we put these explanations in,
or you could say maybe more generously, like we're not thinking about them completely.
Yeah, we're not thinking about them completely.
Because I don't want to necessarily say that in some of these cases that things are being conceptualized or explained incorrectly. It's just perhaps incomplete.
Yeah, it's definitely, it's incompletely. They're not wrong.
Yeah, or there's considerations for any or all of these different processes that would, I don't know, help explain them in a more complete way or what have you.
Yeah.
It's you know,
I agree.
Let me see here. There's a question from C Kim that says, I would like to know the inductance. Oh boy. During EIS at high frequency, like 100K to 10K, the system is simple carbon steel with 3.5% sodium chloride. How to interpret the inductive behavior. So yeah, so usually there's two ways that this is manifesting. One of two ways. One of them is easier. One of them is not. So if what you're seeing at high frequency in your Nyquist plot for inductive behavior, this is minus Ci, this is Z real, and this is 0 here. If what you're seeing is this, and you're asking about this behavior right here, inductive behavior, that's just inductance from cell cables, from it's highly irrelevant, to be honest. You can fit this with a circuit. For this example, for instance, you would fit a leading inductor, a leading resistor, and then probably something like, something like this, right? This is like your standard cell, right? Inductor, ohmic resistance, and then R1, C1, and Warburg or whatever. So this is like the most basic whatever. And basically it's like you're just getting this inductor to fit this tail that happens at high frequency. It's just a result of cabling and stuff that's like not part of your system. Like it's I don't know how to state this more elegantly, so I always say it very crudely. Like who cares?
It's cable inductance.
Yeah, it's cable. Like nobody cares about your cable inductance. Like you can fit it, and then you get your value for L, and it's like it doesn't matter. It's not a part of your real system. It's just like it's not it's not happening at your electrode surface even in some sense. It's like it's a result of the physical connections to your system, and it's just that nothing interesting or useful is happening at your system at frequencies that high. And so you can either fit it, or you can just kind of ignore this data and ignore the inductor and just fit the rest of it and fit the resistor. And then that's where the information at your electrode surface is actually happening. Now, all that being said, if instead you have some odd phenomenon like this, and that's the loop and an induction, that is something happening at your surface, something strange is happening, and it is not irrelevant. If you have something like this, you have a loop, it probably has something to do with different oxidation states of your metal. I think you said you're using some kind of metal, iron, or carbon steel, something like that. Yeah. Okay. So you've got, it's mostly steel is mostly iron. So you've got a lot of oxidation states, and it might be like a multi-step process where the resistances or the impedance of each of those steps has different impedance. And very briefly, from like one oxidation state to the next, the impedance drops, because that's what an inductor does, is the frequency drops and the impedance briefly goes down. It could be the result of some kind of an intermediate species, or some kind of corrosion happening at your steel, briefly causing a nucleation point. There's a lot of possibilities. I've talked about these before, this sort of inductive loop effect and the impact of this and what causes it. And the answer is almost certainly not an actual inductor, but it's some odd confluence of processes. And basically we're forced to use an inductor to fit this in some way, because an inductor is the only circuit element whose impedance goes down as the frequency goes down. And that's what's happening when you have an inductor present, is the phase angle goes up and the frequency and the impedance goes down as the frequency goes down. So those are the two possibilities for you. Like I said, if it's the first one, honestly, like disregard it, ignore it, fit it if you want, but it doesn't matter. If it's the second one, it's some bizarre factor, confluence of factors. And other than it being a little tricky to circuit fit, it's mostly that it's just tricky to exactly explain what's happening. But some of what I just said are the reasons people tend to give, because nobody really knows, to be perfectly honest, why that phenomena happens. But some of the reasons I just described are, the community's best guess, if you will. So I don't know if there's a follow-up to that or not, but anyway, yeah, if you do have any follow-ups to that, please feel free to type them in, and I'll keep monitoring the chat. See Kim, if you have any follow-ups, if you want to clarify, for example, which of those two, processes your induction or inductive behavior is demonstrating, that might be helpful. So let's see here. I think Chris was saying some of the same things I was. Yeah, something about iron oxidation states, additional currents due to chloride reactions. Yeah, that's sort of that intermediate idea. Exactly why that makes an inductor isn't clear, but that might be something for sure that takes it. And then, this is to the point of the whole lights thing. This is one of those scary things that's true, but you almost just want to ignore. LED lights are a terrible source of noise. I would suggest this just in general. Maybe not, because if you do and you discover something, you're going to be very sad and you're going to feel like your whole graduate school is a sham. Go into your lab, take some data, turn off all the lights in the lab, and take the same data again. See what happens.
Yeah.
I hope you get the same results, but I don't suspect you will. I have a friend who's in academia who, it's a couple of years ago, but he was telling me, he was like, for months or even a year, he was trying to figure out what, like, he had some experiments and he couldn't quite get it. I don't remember a lot of the specifics, and I'm not going to like betray the specificity of it anyway, even if I could remember it, which I can't exactly. But it was like, anyway, the long and short is that it was like, couldn't get this thing to work. It was like, why do I sometimes get the results that I want? Trying to like, oh, well, this catalyst is producing this product, but sometimes it doesn't for some reason. And it was like, quite literally it was like the light was out and then the light wasn't out. And it's like, eventually realized like, oh, turn off the lights in the lab, and it didn't work. And then when you turn on the lights, there was just some photocatalytic thing going on from noise or some photo, like,
oh, it's actually a photochemical process
something.
occurring?
Yeah. Something like that.
Wow.
Or it was the whatever,
50
energy,
or 60 hertz noise,
something like that. Yeah. Some electromagnetic energy from the lights in the laboratory were activating something or contributing something. And it's like, well, this is all stupid then. Like, my catalyst isn't the reason this is giving me whatever. Like, maybe there's some photocatalytic, subsequent testing to be done. Yeah. But it's just like, that to me is a depressing thing. Like, whoever thinks about that, right? Just the average graduate student going into their lab in the hood, or they're here, or they're whatever, just testing. When you're mixing chemicals together, you don't think about, I shouldn't have the lights on. Just like, you just have the lights on in the room. Like, who thinks about that?
And that's, folks, is why you need to do a control experiment.
Yeah, exactly. But control experiment with the lights on and off is like next level. So I didn't even think about that when I was in graduate school, and it makes me think that I wish I had, because I would have really been curious, like, what it does to the effect of your experiment. Now, obviously, if you're doing solar cells and things like that, well, it makes a difference because it's a solar cell. But
yeah, you
but like,
don't know what the
variable
is.
Just like a platinum electrode in sulfuric acid, like, it might make a difference. And it's like, oh gosh, you might be very depressed at like realizing if there's any, because it's like anything else, but very specifically to electrochemistry, like we take small changes in things, and that, oh, well, this current is more product was produced or whatever. Like, that's what electrochemistry we're doing. Yeah. And if we're getting small changes and stuff, and it's just because the lights were on, that sucks. But like, does it not? I mean, no. Am I over exaggerating this problem? I mean, I think it's like,
but that begs the question. Like, okay, are you seeing a big change or are you seeing a small change?
Yeah, I guess.
And
it
then
depends,
can you
right?
and like, is the change so small that it doesn't overcome the big picture thing that you're trying to do?
See, that's what I hope is the case in any and all situations of people who might give this a try.
Oh yeah.
And then this specific situation, it was big enough that it was like, oh gosh, that's the reason why I'm seeing whatever difference I'm seeing. Like, it was finally the thing where it was like, literally the switch you change isn't your reference electrode or your counter electrode or your working electrode or your film or your electrolyte. It was the light switch.
Yeah.
Creates like repeatable solution in your results or whatever. But I do think and hope that in a lot of situations, the answer would be what you said, where it's like, yeah, but there's a difference, but it doesn't change the overall picture.
Yeah.
But I think that there are situations where it does make more of a
Oh,
difference.
oh yeah, but this also
And
happens.
nobody thinks about it.
I think this happens way more frequently. Not necessarily just like light switches and LED noise, but the fact that a very, very small thing that you never even thought about is actually causing an error.
Yeah.
Like, I mean, we were talking about this, like, we discovered this maybe like a month or two ago, the whole like reference electrode shunt. And the idea is that there's capacitance in the glass of the reference electrode
Yeah.
that creates a capacitor. It's like a 8 picofarad capacitor,
Mhm.
super, super small, but holy cow, at the high frequency, it has a high impedance and it creates artifacts in the high frequency regime
Yeah.
for EIS. And just like kind of case in point. And similarly, I worked with people who were doing like CO2 reduction experiments and like photo electrochemical CO2 reduction experiments. And I say, do the experiment with absolutely no CO2 and see if you get some carbonaceous product. Because then like you must do those control experiments.
Yeah.
Otherwise, it's like, yeah, it's due to something totally different. Your catalyst or whatever has contaminants on it, and it's a big headache for people. Sometimes it can take like a year before they really figure out what's causing the problem.
You can
So,
figure out something in a year? Jeez, that's fast.
I'm talking about figuring out a contamination problem in a year.
I was just thinking anything in general.
Anything
that's
in a year.
impressive. Well, anyway, that was
That was a good discussion. Hopefully people found that
Yeah.
helpful.
I mean, the long and short is electrochemistry is terrible and we should all stop doing it. Okay,
Yeah.
next question.
Okay, next.
Which fitting model should be used when doing impedance on lithium-ion electrolytes? Well, first of all, I'd have to that's a question that's very specific to your data, right? I'd have to probably see your data specifically. Quite often, and in your question seems specific to electrolytes, and so I also don't know 100%. What you're studying. For example, I mean, are you studying just the electrolyte, or is it in the context of a battery itself?
Yeah.
But for example, very often, a lithium-ion battery looks something. A battery itself it might have some inductive craziness. I'll just ignore that for now. But it'll often just be like this, or like that. And so your model is usually going to be something like, I use a CPE because it's almost never even remotely ideal capacitive. Usually have your alphas be quite small. So that would be something like that. Very simply, right? We'd have our whatever ohmic resistance and then charge transfer resistance. And then usually it depends on like the battery. Sometimes it depends on the state of charge. But the blue one would just be where you have another one of these. You might just have two. So this would be Q1 and this would be Q2. So you might have two. Oh, sorry, I neglected a Warburg element or something. My fault.
Happens.
Whatever. There should be a Warburg or another CPE here. And so essentially, if you have multiple charge transfer processes, which you often in reality do, you might just add another Randall's element. So this would be one semicircle and then two semicircles, right? And typically this would be like anode SEI, this would be cathode, and then you'd have diffusion stuff. So sometimes there's three. It depends on the battery. That's a battery generally. So when you're talking about electrolyte, again, it's sort of nebulous here because I don't know what data you're talking about. I'd have to, if I saw the data, I might be able to suggest a model depending on what it looks like. But often one of the things that you're doing when you're testing electrolytes or like membranes is you're looking at conductivity. And so a lot of times it's actually a more simple system than that. If you're just trying to study the conductivity, you might just be getting like high frequency resistance and then relating that basically, it's kind of the inverse of resistance is what conductivity or conductance or whatever the right unit is, right? But in some manner of speaking, it's like if you're just getting the conductivity of an electrolyte, for example, you might not have any circuit model at all. You're just taking impedance at some high frequency and using that to calculate the ohmic resistance or something like that. But that's a very general, without the specifics of any data that I'm seeing, answer to your question about, lithium-ion circuit models. Let me see. Yeah, all models are wrong. Some are useful. That's true.
That's true. Yeah.
All models are absolutely ridiculous.
Yeah.
But they do sometimes help.
Yeah.
And everybody likes to put them in papers because it makes you look smart.
Yeah.
So yeah, that's true.
There could be they're convenient.
Yes.
Circummiles
Just to be clear,
convenient.
we are all constantly saying nonsense. All of us, all the time. That's just the reality. And so I just don't feel the need to justify your nonsense. Just be proud. Be nonsensical and proud. That's my advice for you. Let's see. Train on silver nitrate and you'll think about lights. Yeah, I guess is silver nitrate really photoactive? I guess it must be. Yeah, silver, even like silver chloride. If you have a silver chloride reference electrode and you leave it out in the sun too long, it'll get all messed up.
Yeah.
Yeah. Silver chemistry is quite.
That's interesting.
Yeah. So it's like slowly photoactive, but it's photoactive. Like after if left long enough, its oxidation state will get all wonky. Is it something like that, or does it tarnish? I don't know exactly what happens, but I know, for example, like you don't want to have your silver chloride or whatever electrode in sunlight for too long. It can get all messed up.
Yeah, definitely silver chloride reference electrodes will change and look weird if they're left out in the sun.
Yeah, I don't know exactly what happens to it, but something
But
happens to it.
Similarly, I don't know exactly what happens to it, if it's some kind of oxidation or an excited state process or something like that. Yeah, I don't know what happens to a silver ion.
Yeah, I don't know exactly.
Like
I don't know what the process is like chemically. All I know is that something happens that's not good.
Yeah,
right.
That's not
it
good.
Changes and you don't want it to. Yeah.
It's probably it's probably forming like silver oxide instead of silver chloride.
Oh, that makes sense.
Probably what
I guess.
it is.
Yeah.
I thought that. Yeah, reacting with oxygen.
Yeah. Daniel commented from the Mott-Schottky here. So you said, yeah, you've mentioned frequencies. Some papers recommend low frequencies. In my system, I can get analytical measurements at 5 hertz, but not 10 or 1. That's odd. You can get 5, but not higher or lower. I'm not sure what that means. It's a bit strange. Generally, you shouldn't need to go that low either. So it's really that middle sweet spot. So something like if you're using 10 as a 10, you said you can't get 10 hertz. I guess I don't totally understand why you can get 5 but not 10, and you can, is there some I guess I don't know what instrument you're using, and it'd be straight, usually there'd be a cut, like, can you not get lower than 5 but you can get higher than 5? Anyway, the point is that if you start at like 1 to 10 kilohertz and go down 2 or 3 decades, that's probably sufficient. You don't usually have to go to like 1 hertz or like millihertz or anything like that. You don't usually have to go that low. The behavior you're after with the line indicative of capacitive behavior will start usually at the mid frequencies, like a kilohertz, in that range, and then 1 or 2 decades is probably sufficient. It's just the idea that you don't really want to do just one frequency. Even 1 decade of frequency is better than none, like better than 1 point, because it's just a more accurate method of measuring capacitance. So I do recommend that, even if you have somewhat limited instrumentation availability, I suppose.
See, there's a little bit of discussion back and forth.
I'm not sure. Interpret types of cell degradation and failure. I'm not sure if this was a comment to something else or this is.
Yeah, if you can, right now that just sounds like a comment. It doesn't sound like what is the question? Vish, I know you mentioned this 2 times. Interpret types of cell degradation and failure, but and when you say cell, what kind of cell are you referring to? Just a generic electrochemical cell?
Yeah,
talking about a battery. Talking about a biological cell.
This is also an example of one of these very general questions. If the question is something like, how do I interpret cell degradation and failure by electrochemical and physical methods, like that's a PhD thesis. Like, you could have a PhD thesis titled Interpretation of Cell Degradation Methods and failure by electrochemical and physical characterizations. Like that sounds like a PhD thesis title. So
Yeah.
this question is certainly a good like thought or question in some sense, but it's also far too broad. You would have to, if you have a specific question therein, please feel free to.
So he says a lithium-ion
Right.
cell.
Okay. So again, in general, my first answer to your statement or your inquiry is that yes, lithium-ion cells will degrade and reach failure by electrochemical and physical methods, or over the course of their usage. But if it is not exactly, it's quite an undertaking to start describing every single physical and electrochemical destructive and non-destructive method through which those are conducted. For example, I spent 2 years in a postdoc studying mostly destructive, but partly non-destructive methods of characterization of electrochemical and physical. I literally did this in my postdoc, and I spent 2 years doing it. So please get a little more specific if you'd like. If you want me to talk about something specifically.
Doesn't know about lithium cell degradation testing, just the basic stuff. So,
yeah.
So like, okay, so for example, Neil, you did EIS as a way to determine, to see whether or not your lithium-ion cell was degrading. That was just a technique, and you could see, did the resistance increase, or I guess you have a very low impedance if the cell is good, and then you have a very high impedance if the cell is bad.
Again, this is a long discussion. Not necessarily, but sometimes yes. But it's often it's more basic that can be depending on state of charge. For example, a battery has a very low resistance at a high state of charge because it's very easy and ready to give energy to you. And at a low state of charge, when it's fully discharged, it has a very high resistance because it's harder to give energy when it's tapped, right? When it's discharged. In studying cell degradation,
well, he's just looking at the techniques, right? He just wants to know, like, EIS is a technique, a non-destructive technique.
I mean, non-destructive and destructive. Yeah. So like, okay. So EIS is probably the most, I don't say popular, but one of the most accessible non-destructive techniques to study lithium-ion battery cell degradation and state of health in general.
Yeah.
It's a very non-invasive, non-destructive technique. There are in general charge discharge, galvanostatic charge discharge, or slow scan cyclic voltammetry, or just open circuit monitoring are also somewhat non-destructive. They can be more destructive if you overcharge or over discharge, but generally speaking, most electrochemical methods can be relatively non-destructive and non-invasive to study the degradation of a battery, because you can do charge discharge and you'll see something crazy, and that indicates that there's degradation, but you're not really being too destructive. Again, if it causes further destruction through over discharge or overcharge, that could be a problem. And then destructive testing are things like puncture, heating, crushing,
kicking,
punching, fighting, biting,
yeah, flamethrowers, bazookas.
Yeah, exactly. Yeah, so
those are all the destructive techniques.
Those are some of the things that I studied when I was a postdoc, actually, different methods of causing a battery to fail. So quite literally strapping a heater to it and heating it until it explodes, putting a nail through it, puncturing it, watching what happens, overcharging it, but that doesn't always work because commercial batteries have safety features that prevent failure during overcharging. But those are ways to induce it. And then, the testing, again, this is like a big topic and I'm just trying to cover skirt the edges of it, but like people do, it's called DTA or DP. What is it? Destructive physical analysis, DPA. So basically a cell dies and you cut it open and look at it. It's just a fancy term for that. It's just like surgery on a dead battery. And then any and all physical characterization techniques can and are used in these situations: SEM, TEM, XRD, XPS, EPD, what is it? ICP,
Like ICP-MS.
ICP. Is that whatever?
Inductively coupled plasma mass spec.
Yeah, so that's more of an elemental.
That's an elemental analysis technique. Mostly
yeah.
for solutions.
Right.
But,
yeah.
yeah.
But you can just sometimes you take the stuff and you dissolve it in a thing, NMR, whatever. Like all of those are used sometimes as destructive physical analysis after a battery, ex situ kinds of analyses, to see, oh well, what happened to my anode or my cathode, my electrolyte.
Yeah.
What happened to it? Did it change phases? Did it aggregate? Did it deaggregate? Did it all kinds of stuff? There's a million different answers to that, right? But yeah, okay.
I've also been hearing about Raman being used to as a non-destructive technique for studying batteries as well. So, but I would talk to Hariba about that, as they are the ones who, most Raman companies may have some kind of accessory to actually study a battery or parts, some depth into the battery. A Raman laser can actually get some information out.
Doesn't penetrate through every material, right? Or does it? Is it surface reflective?
It's a surface penetration. So like,
how far does it penetrate?
It depends on the wavelength of light.
Okay.
So so usually most Raman techniques use like a 532 nanometer laser or 633 nanometer laser.
That seems like it would penetrate pretty well, right?
And so to a degree, like
smaller wavelength is higher energy. So
yeah. So if you have a 532 nanometer laser, you can try to focus. You can actually focus the laser light through the thing. You'll get a lot of reflection, but with Raman, you're looking at a very small number of photons that get Raman scattered. And in some cases there's another technique called Caesars, which is like, it's like spatially offset Raman scattering, which has even lower detections, but it's non-destructive. You're shooting a laser that doesn't generate enough heat or anything to try to get some signal. So that's another technique, but something to at least learn or know stuff about.
I'm gonna finish this chain with Animesh here, and then I think there's some questions above. There might have been. Did we miss anything? Oh, sorry. Anyway, so Animesh, in EIS we can't know which part of the cell has problems. No, you can. It depends. So, for example, in a typical battery with no reference electrode, your EIS includes both the anode and the cathode. So a 2-electrode setup with a potentiostat means you are fundamentally getting results from both electrodes, both the working and the counter, or the anode and the cathode, however you call it. And so actually in this case, when you're doing a 2-electrode, which is often what you're doing, experiment with a battery and you're doing EIS, you actually are able to individually, assuming that they have disparate enough time constants, you are able to analyze the anode and the cathode separately. And so sometimes you can tell if the resistance, for example, of the cathode has grown hugely compared to the anode, the cathode might be having problems or something. Or the data in a particular frequency range would be more correlative with one or the other. And so that is the thing. On the other hand, with reference electrodes, for people that work with cells, and this is talk about a destructive technique, is that sometimes you jam a reference electrode inside of a battery. It's pretty destructive, but it can allow you to study one or the other anode or cathode individually. And when you do a 3-electrode experiment, you are necessarily not getting data from the auxiliary electrode. So you can get specific impedance data or whatever voltage, potential data, current, whatever, on like just the anode or just the cathode by using a reference electrode. And that means you are necessarily ignoring the other one. You are not getting an impact. That's a fundamental potentiostat circuitry thing. So yes, you can, but it's not always perfectly obvious in some cases. And that just comes from discernment of the data. But in general, yes, in EIS, you can sometimes know which part of the cell, generally speaking, anode or cathode, or SEI, for example, is behaving differently compared to its original state, I guess. And then I guess your last question here is that which part of the battery is most likely to fail first, electrodes, electrolyte, or separator? The real answer is it depends. Somewhat imprecise and general answer is that it's electrodes and separator. Electrolyte doesn't fail. There's nothing about electrolyte in a battery that is likely going to fail. But what will happen when and if a battery fails is that most likely either one of the electrodes gets a problem, or the separator becomes compromised. And in both of those situations, often what happens is you get a short between anode and cathode as a result of the separator being punctured, or a manufacturing defect, or a dendrite, or I mean, any of a couple of other some other things that can happen. And then once that happens, you have a huge generation of current from an unrestrained and unregulated electrochemical or chemical reaction that occurs, and that tends to eat up electrolyte, heat it up. It's called thermal runaway, and then eventually the electrolyte is the fuel, and that's why it's also difficult when batteries start going off. They can't really be stopped very easily by traditional fire prevention methods, because it's a self-contained fuel source. The electrolyte and the electrodes themselves are fueling its combustion, and it will go until it exhausts the fuel source. Let's see.
There's
Daniel had another system can only afford low frequencies from 1 to 500 hertz.
This was I think conversation between Chris and
Daniel.
Yeah,
he was just more about the range of frequencies for the Mott-Schottky,
yes.
But so yeah, looks like we've at least gotten to some place for you to start trying some things, Daniel. So hopefully that's reasonable for your Mott-Schottky. You'll be able to get some decent results.
Mm-hmm.
And you don't need a fancy software like ours, although it is terrific. But you don't need a fancy software necessarily to do your Mott-Schottky analysis. You can set a potential, do a quick impedance thing, set another potential, do more impedance.
Mm-hmm.
You can do the analysis that way as well, separately, and calculate it yourself for sure. Mm-hmm. As well. Let's see.
Next we have Axel Eriksson. Not a really technical question, but he's a PhD student working on PEC devices and
photoelectrochemical.
I think so, photoelectrochemical devices. And you get the feeling there's so many electrochemical techniques and ways to analyze the data. How do you keep track of everything? I don't know. We've just been doing this for a super long time, and then to a degree, once you understand the basics of like what a potentiostat does, or just applying a potential or applying a current, you kind of like it's really just rearranging a lot of the same stuff. Like you can determine the diffusion coefficient using so many different electrochemical techniques. It's kind of ridiculous, but I think we've just been doing this for a long time.
Yeah,
it just becomes second nature to a certain degree. And you're a PhD student. You're learning all this stuff. It's all very new. So yeah, we just keep working at it. Really, just keep working at it.
Yeah, and then there tend to be just things that it's different for every specific topic. Like photoelectrochemistry might be a little different than battery or fuel cell or solar cell or what have you, right? But there's a certain set of tests you're probably going to just be repeating every time you set up your cell. Like you'll always start with an open circuit potential to just characterize the system, make sure it's connected properly and everything's good. You might always do a quick CV to just get a lay of the land, see what processes are occurring where and things like that. So you might sort of keep track of them by having a sort of simple list of 2 or 3 different experiments you're always going to run after you've set up your system as a means of just initial characterization, making sure everything's all happy, right? And then you go from there, and then all the more complicated ones, if there's other ones people are doing, pulse and impedance and all this other craziness, right? Then it's like, those are beyond the initial, simple ones you're using to like get started or whatever. But yeah, I mean, really, just like Alex said, it's like it is one of these. The more you do it, the more you'll just have that experience and knowledge of all the different techniques. And listen, we work at this company, and I also at times forget, like, oh, DPV, which one's that? Is that the one that goes, the bottom goes up, or the bottom stays the same, and the top one goes, like, I don't always remember either. I have to look up stuff. Like, we don't even 100% remember every technique off the top of our head at every moment. Like we also, it's
we have to look them up. And luckily, once you look them up, you remember.
And then you remember, that's why this is what you do with that or whatever. Yeah. So that it's also, a reasonable answer to say, you don't have to always keep track. You don't always, you'll, getting a PhD is the beginning of your career of learning, right? I mean, honestly, like, you're be prepared to constantly be learning new things and be open to that, right?
Mm-hmm.
So,
Daniel, Camero has another thing, just about our Electrochemical Studio simulation software. So you can request a demo. So if you just go to our website, you can go to the contact us and just ask for a demo. And we usually have like 1 week trials. So just go to aftermathlive.com, contact us, and then fill out the information. And one of our colleagues or ourselves we usually have like 1 week demos for certain license versions. So you can definitely do that. Just like tell the PI, about it and give it a shot. Let's see. We just have this person who looks like they did a school project shaking a magnet in and out of a coiled wire trying to get a light bulb to turn on, but nothing worked. If you're in school and you're trying to do this stuff, it's hard.
How stupid were we? That's not a good question.
It's not a good question.
That's also not that stupid. You have you have a magnet and a coil. You fundamentally understand Bio's law to some extent if you're doing that, right? That's the curl thing, right? A magnet. The hard part about what you're trying to do is that, like, in theory you can induce a current by moving a magnet, but like you have to recognize, like, the kind of commercial magnet that you can buy is not strong. Like, it's just not possible to buy a magnet with really high strength such that you could like calculate it. It's probably hard to know exactly the magnetic strength of like a magnet you can buy from Amazon or something, right? But fundamentally, if you did the math out or whatever, it's like you would either have to move it so fast or something, right, to induce based on Bio's law, right, or whatever, or you'd need a big enough magnet, or like 500 of them or something. I mean, it's like, you're not stupid. It's actually a tremendous idea.
Yeah.
It's just, and then there's other parts of it too, which, like, if that makes you stupid, then I'm pretty stupid too, because I've had times where I've been trying to like come up with demos, for example, in my office, for like, oh, can I show how, this solar cell or this battery, I can show people a thing, in a webinar in a setting like this or whatever. And it's like, I'll use a LED or a bulb or whatever. And it's like, not every LED has the same like rating. Like, they need a certain voltage above which it won't light. Like, if you don't provide enough high enough voltage, it won't light at all.
Yeah.
Right. And so sometimes it's like, maybe you're getting a little bit of current through it, but the voltage isn't high enough and it won't light.
Yeah.
So like, there's a lot of stuff there. It's like, there's electronics, there's practicality problems,
yeah.
or like Chris says, you need a lot of coils.
Yes.
Yeah. Or a really fast moving magnet, or a much stronger magnet. Like, yeah. So no, you're not stupid. You're thinking like a scientist. So, and in the future, just get a stupid potato and stab it.
Yeah.
The potato light bulb works, I think.
Yeah, yeah. I think it. I
right?
think it works.
Just if
I
you
think
do
it does work.
yeah,
Yeah.
it's because
Soak it
it's
in
it's just electrolyte.
Yeah,
So
yeah.
if you just stab 2 wires of a light bulb, again, it depends on the light bulb, into a potato though, it'll generate. There might be more to it than that. I don't really know.
Yeah, I haven't done enough of it.
I actually never did the the potato light bulb thing.
Yeah, me
You can
too.
do it with like an apple. You can do a potato. Anything
probably.
anything that's basically like has sugar, electrolyte, right? Like star. It's just the internal is an electrolyte basically. So it's it makes a pseudo electrochemical system
Yeah, yeah, and
it creates a path for current. So.
yeah, that's right. It's like
Kinda fun.
some potential or something.
Yeah,
like
I
that.
don't know exactly where the potential comes from.
I'd have to look it up.
I don't actually know where potential comes from in a potato.
Yeah.
Potatoes have a lot of potential though. Like if you mash them up, they make great mashed potatoes. So like there's a potential for potatoes to be delicious, is what I'm saying.
Yeah, yeah.
This may not be electrochemistry anymore, but Thanksgiving's coming up.
That's right.
So
That's right.
so if I can bring this full circle.
Yeah, yeah, that's right.
It's that the potential for good food is infinity.
It's infinity. Yes, yes.
That's pretty funny.
Let's see, just a few things. Oh, Daniel, I didn't realize you were the PI.
Oh, perfect.
So great. Now you know how to how to get in touch and and request a copy
just
of
contact
it.
us.
Through the contact us
like Alex
form.
said, yeah, on the Aftermath Live, or you can just send us an email.
Yeah.
Contact us on our main website or on Aftermath Live. We can certainly help you with that, and I can also have more offline discussion about the Mott-Schottky stuff if you want to, me to show you a demo of how ours works, or just any of that kind of stuff, or any of the analysis, because I kind of described it, as best I could in this setting. But if you had more sort of questions or whatever, I'm happy to kind of talk about more about that with you. So reach out if you'd like.
Yeah.
Let me see here.
It looks like no other questions. A few comments. A good chat.
Yeah, we appreciate everybody.
Yeah. Yeah, we definitely appreciate the conversation. It looks like Chris is running into a small technical issue right now.
It's because YouTube is a small independent company.
Yeah, that's right.
They don't have resources to make things work well. So sorry about that. We'll try using a bigger company next time.
Yeah. Let's see. I don't see any other questions. Or any specific topics.
I think we got to everything.
I think we got to just about everything. We're glad that everybody appreciates the channel, the YouTube channel, and and stuff like that. So
we hope that you'll watch our podcast coming out soon.
Yes. Yeah. Yeah.
It's just educational enough, but mostly entertaining.
Yeah, that's right.
So hopefully you can listen to it while you're in the lab, doing your thing, and it won't either distract you too badly and give you a little bit of a laugh.
Yeah. Yeah. Let's see. We got a new question from Varanasi Ramanch. If we got that right. Can you comment on how to evaluate electrochemical band gap of a material? So there is no such thing as an electrochemical band gap. There is just a band gap of semiconductor materials. And really the best way, and this is still something that I am trying to wrap my head around, but really the way to figure out what the band gap is of a material is to do a light based technique. You need to, and the system itself, the type of semiconductor. So you can have a generic semiconductor that has a band gap. You can have it doped. That also has a slightly different band gap. And then when it's in contact with solution, it also looks different. The structure of the band gap looks different. There are things like bands that can bend in electrochemical systems. And really, I would recommend using like a spectroscopy technique or a light related technique to determine what that band gap is. I don't think there's really I've talked to some people about like trying to evaluate the band gap using electrochemistry, like CV or something like that.
As far as I know, there's no way to do that.
Not with CV.
Yeah.
I think EIS.
There might
you
be
can
with
get the flat
Mott-Schottky.
band
So yeah, so
potential,
I don't
yeah.
is that I don't know. That's I guess that might be related, but I don't know.
That's true, because the flat
Right.
band potential is not the band gap
No.
per se. No.
I have a really hard time conceptualizing what flat band potential means, to be honest. It's the like when you try to look up the definition, it basically is like it's the potential where the band is flat. It's like well, that's just a circular definition, right? It's like that doesn't help me at all. I don't know what that. I still don't know exactly what that means. Like the band, like the what like what makes it flat? Why is it? When is it not flat? And why? Like I don't 100% know, to be perfectly honest. But it's possible that something like a Mott-Schottky experiment, which basically helps you evaluate a semiconductor's properties through the determination of things like the flat band potential and the electron donor density. The electron donor density isn't related to the band gap per se. That's more of like how many free electrons it has, NRP type, if it has holes or it has excess of electrons, it's related to that. The flat band potential probably does have a relation, but yeah, I don't know exactly if it's related, and from the eventually, like the calculation of the band gap is like however many electron volts, right? It's like that's
Yeah.
like that's what a band gap is. It's in like
Yeah.
the EV, and it's like I just don't know if there is a way, and if there is, what the calculation entails
Yeah.
from like either flat band potential, Mott-Schottky, or whatever, or any other electrochemical. I think probably you're right, Alex. It's mostly a photo or a spectroscopic technique that would be required to measure,
Yeah.
energies of that level or what have you.
Yeah. Yeah. I think so. Okay. Let's see. All right, Chauncey, thanks for stopping by the stream. From looking at our YouTube videos, we try to do these every Friday, except for next Friday. but yeah, come on in. And Chris has made a comment. The band gap is essentially the discrete difference in potential between the excited state and the ground state. Yes, and you can't move. And you can only move between those two bands with light, like like you can't use a potential to like get the electron to jump from one of those to another. You need to use light, I think, to get that jump. And when you see that jump, it shows itself as like a photocurrent. So but that's all I know. That's all I know about it. I wish I was talking about how can you get people to learn about this stuff a little bit better. Like, it's relatively easy and safe to do like a cyclovoltammogram of ferrocene in a lab. Like, you can get people to do that, but there's like, to get a good semiconducting material that doesn't have a native oxide layer, you have like, to get rid of it, you need to use like HF and all kinds of stuff. Super dangerous. Not for like teaching purposes, but there may be
HF scares the pants off of me.
Oh yeah. It's definitely a very worrisome thing. You want to be very, very cautious about that. But but yeah, there's a lot of stuff about that. But yeah, I don't know enough about it. Dan Shearson was mentioning like this selenium oxide could actually be a stable air sensitive semiconductor that you could do experiments on. And of course, just Dan Shearson just selenium. Like, oh, okay, apparently selenium has semiconducting properties. You can study it or something.
The only thing I know about selenium is it's in shampoo.
That's
it.
That's it.
I'm a chemist. That's the only thing I know about selenium.
Yeah.
It's in shampoo.
It's in shampoo.
That's it. It's the only thing I know. It makes my hair silky and smooth.
Yes. Okay. All right. So I think that's it. I mean,
yeah, I guess so.
We got all the questions. About to jump off into a Thanksgiving week, sort of say.
For all of those of you who are in the US or celebrate, our Thanksgiving holiday, I hope you guys all have a good holiday next week, next Thursday. And yeah, we'll see you in 2 weeks.
Yeah, 2 weeks.
And then, as Alex said, we'll be at the Materials Research Society meeting, MRS, in Boston the week of the 27th, just after the holiday.
Yeah.
So if you are there, come say hi to us at the booth.
Yeah.
And otherwise, I hope everybody has a good weekend and a good holiday, and we'll see you next time.
See you next time.